Welcome to Module 8 in our series on artificial intelligence. This module presents a brief review of optimization for machine learning. Specifically, this module will teach us about mathematical optimization as a precursor for the next module on gradient descent. I want to begin with a question, specifically what is mathematical optimization and how does it relate to supervised machine learning? An optimization problem is one that asks us to systematically find system parameters that satisfy some practical constraints as well as maximize positive characteristics, for example efficiency, and minimize negative ones, for example cost. One prime example is the traveling salesman problem that I think many of us are familiar with, and it asks us how do we visit all the cities on the map while traveling the minimum distance and ultimately spending the least amount of money. In short, mathematical optimization asks us to find the best configuration of a system or the best solution to a problem. Now, like we've said already, this module addresses optimization. It's a topic that we've covered extensively in other lectures, and we can see these threads woven throughout the last 7 AI modules. Here, we emphasize the aspects of optimization most relevant to machine learning, as that's the focus of this series. As stated previously, mathematical optimization searches for system parameters that maximize desirable characteristics or attributes as well as minimize undesirable ones. For example, can we build a car with high reliability and high speed with low weight and low cost? Generally, the optimality of a given characteristic is dictated by an objective function or a cost function. In essence, optimization concerns maximization or minimization of a real, quantifiable function that compares actual system behavior to that which is desirable or ideal. Next, there are some terms or characteristics that I'd like to review before we jump into examples. The first is a comparison of continuous versus discrete optimization. A continuous optimization problem is one that uses continuous functions and parameters. Pretty self-explanatory. And as we would expect, a discrete problem is one that utilizes discrete functions and parameters. Now, discrete problems may be simpler to solve or seem simpler to solve because only a finite number of possible system configurations exist, unlike continuous problems that present an infinite number of possible solutions. However, discretization can introduce challenges, such as reduced precision or increased sensitivity to small parameter changes. I'd also like to compare constrained versus unconstrained optimization. A constrained problem places no restrictions on how an optimal solution is defined. This allows us to choose a true globally optimal solution. For example, how do we minimize grocery spending if there are no constraints on that problem? One solution is to simply not go shopping, right? That would spend no money and the output of our cost function would be 0. Or to extend that idea even further, right, we could take food from our fridge and sell it, and that would yield a negative output, even smaller output from our cost function. Now, this solution allows us to find a globally optimal solution, but ultimately it